Welcome. This topic is called Water for Life and is part of the Chem 100 Excel online course. Water is the most abundant substance on Earth and it covers about 70% of the planet's surface. And water has been called the beginning of life, the basis of life by those who believe evolution began in the oceans, and water continues to play a key role in the cycle of nutrients, and that is how animals, plants and the earth exchange nutrients. Now, people can't live without water. Every living cell, including those in our bodies, every living cell requires water. So we're made up of about 60% water, and if we were to lose about 2% of our body's water content, we'll begin to feel thirsty. And if you were to continue to lose water, not rehydrate yourself, not drink water, you're going to feel the symptoms of dehydration. And that would include things like dizziness, you get a headache, and you get that body ache and fatigue. So while humans can live for about 6 weeks without food, nobody's been known to be able to live for more than a few days without any water at all. That's how important water is to our body. And there's another thing about water. So unique amongst all substances that we know of, water is commonly found, okay? Commonly found in all three states. So we're familiar with water as a liquid, but yes, we also are familiar with water as a solid, and that's ice. And every time we boil water, it generates steam, which is a gas. And water also has a high specific heat. And what that means is that each gram of water can hold more heat than most of the substances. So that means lakes and oceans, large bodies of water, they're very good as heat reservoirs because water can hold heat. And that means lakes and reservoirs, they play a critical role in temperature and in climate control. So another unusual and extremely important property of water is that the solid is less dense than the liquid. So ice floats on water. So this density anomaly, this unusualness about water, means water has the greatest density in the liquid form. In fact, about 4 degrees, which is warm enough for fish to live in. So as you can see in this picture, in a lake, when the top is frozen over, the water at the bottom is still warm enough for fish to live in. So in this topic, we're going to cover a lot of materials because water is so essential to life, and not only essential as a basis for life, but we use it in everyday life. There's a lot to cover, so what we'll do is we'll group the material into just 3 sections. And if this topic interests you, you're encouraged to read more about this, learn independently, and then come and share your findings with the class. I'm sure we can meet online for further discussions. On to the first topic then. The first topic looks at the molecular structure of water because this will give us a basis to understand the unique properties of water. And then the next section will look at water as a natural resource and what are the issues whenever we are using a natural resource. For example, water distribution, overconsumption, and inefficient use. What I do now then is give a brief summary of each section, and then along the way we'll list questions you'll find answers to in your study from a chemistry perspective. So online you're going to be directed to more resources to help you go deeper into each issue. So to understand the unique physical properties of water, we've got to begin with its molecular structure. So in this first section, we'll look at the chemical composition and the structure of water molecules. The chemical formula of water is well known, H2O, meaning it's 2 hydrogen atoms bonded to a central oxygen atom. So the arrangement is, imagine a letter V. So you've got oxygen, okay, this is an upside down V. You've got oxygen at the, where the 2 lines, the 2 bonds meet, that's oxygen, and hydrogens are at the end of it. So oxygen molecule is in a V shape. Now oxygen and hydrogen atoms, they have very different electronegativity. And that means the electrons they use to form the bond holding the atoms together, the electrons are not evenly distributed between the hydrogen and the oxygen atoms. And that makes each of those bonds polar. And what that means is that the water molecule is effectively a tiny, tiny little magnet. It behaves like a tiny little magnet. So hold on to this thought, because this explains two unique properties of water. First of all, it's a liquid at room temperature and normal pressure. Because you see, the polar molecules, these tiny little magnets, they have enough attraction such that in a sample of water, the molecules are close enough to each other that they form a liquid. Okay? Otherwise, if there's not enough attraction between the particles in a sample, it would be a gas instead. Okay? So water is a liquid because of that stronger than usual attraction between the molecules. And remember, without liquid water, life on Earth would not be possible. Then the second thing is that at colder temperatures, these water molecules, these little V-shaped magnets, they arrange themselves in a crystalline arrangement. Now, you go into the details when you study this, but essentially, these V-shaped molecules, they form a three-dimensional lattice structure. So the attractive forces in ice between these water molecules, they're still hydrogen bonds, but the V-shape of each water molecule makes them want to create a very open structure. They have to align in such a way such that the magnets are aligned. Okay? So ice is a very open structure on the molecular level. And if you have a very open molecular structure, what you end up with is something which is of lower density. Ice is less dense than water. Okay? So icebergs. Icebergs float on water because ice is less dense than water. So in this section, you'll study the details of this simple overview I've just given. What about water as a natural resource? Well, unlike coal and natural gas, those are the examples of fossil fuels, water remains chemically unchanged throughout its cycle. So as it cycles through the natural environment as rain, groundwater, evaporation, condensation, etc., and as we use it in our homes and farms and factories, water remains essentially unchanged. At the end of it, it's still water. Okay? But when we use fossil fuel, just to show you the contrast, when we use fossil fuel, we burn up that fossil fuel. The fossil fuel is consumed as it's changed into electricity or light or heat. Water is chemically not changed because it usually functions as a solvent or a carrying agent. Now, there is a caveat there. Water is chemically changed whenever it's involved in a biochemical reaction, for example, or in any chemical reactions we carry out in laboratories, factories, chemical plants. But the amount of water used in that way is insignificant compared to the amount of water cycling through the world. Okay? To put it another way, the amount of water we have in the universe since its beginning, we still have pretty much that much water. Okay, so water is pretty much unchanged throughout the course of history. You may have heard something gross like that, Caesar's pee, some molecules of that may have ended up in the water you drink today because water is actually not destroyed through as many uses. I digress. The point I want to make is water as a natural resource is not, so for us to use it, it's not how sustainable it is, but instead it's how do we distribute it? How do we make sure it's clean and safe? Okay? Because it's not just water we need, but clean and unpolluted water. Okay? Once again, let's just reiterate that. Not only is water essential to biological life, but we also use it in so many different ways in our everyday life. Okay? So in the US, for example, households use about 10% of water, compared to, say, 20% for industry. And by far the biggest consumption of water is agriculture, that accounts for 70%. So between homes, industries, agriculture, there's everything that we do. In every walk of life, we use water. So in this context, you'll learn in this section things like what is safe drinking water, what surface water what's groundwater, and what's this concept of a water footprint, because in our use of water as a resource, we're beginning to develop ideas of a water footprint, analogous to, say, a carbon footprint. And also, since there is a growing mismatch between where we can gather water, where water is located, and where people actually need to use it, we have to think about water distribution as well. Now, if you live in California, you will know that we're going through a severe drought, and has been for some time. So how do we manage that? How do we responsibly use, distribute, and take good care of our water supplies, especially in the, in the face of a drought? Okay. One last topic. Okay. As climate change and affect the supply of water, what are the issues and the challenges with that? So there we'll look at not water as a resource, but the challenges of a resource that is unevenly distributed. What are the challenges of using water as a resource? So what are some of the personal and communal and even global efforts to reduce humans' overconsumption and inefficient use of water, which is an amazing and precious resource? Hopefully you see how chemistry is again fundamental to understanding something so important and so wonderful as water. Thank you.